everyone, thank you for watching this video. I am Agustina. I am going to tell you a little bit about this work that's a specific subshot noise transmission measurement proposal. So when you model light going through loss, what you usually do is to study a beam splitter, and if you compute the variance of the output number of photons, what you find is that it depends on the input variance of the number of photons. So what you want to have, if you want to achieve the highest possible precision, is the lowest possible variance in the input light. So what we propose is to use a specific single photon source that we are building in our laboratory, and we call BinMux XSP. So this is what the source looks like. It has a per generation stage based on spontaneous parametric down conversion in a nonlinear crystal, and then it has a time multiplexing stage that both raises the single photon probability and also synchronizes the output photon with an external clock tick. You can find more information about this work in this previous paper. So what we did here was to propose for a direct type of transmission measurement this specific single photon light source. We built estimators both for number resolving and threshold detectors. We computed the mean and the mean square error of these estimators, and we compared it with the shot noise limit that's achieved using coherent states as input and number resolving detectors, and with the ultimate quantum limit that's achieved using ideal Fock states as input. So what we found for number resolving detectors is that if we computed the mean square error radio with the shot noise limit, so if we have a radio that's higher than 1, that means subshot noise performance, we find that for an input mean photon number of 1, we have for the whole range of transmissions radio higher than 1. These different lines corresponds to different complexities of the time multiplexing stage, so what we find is that we have an optimum situation. We can achieve radios that are up to 1.4. Also, if we see what happens for a given transmission and we vary the input mean number of photons, we find that we can improve even this situation. For the threshold detectors, we can also find some situations in which we have subshot noise performance for an input mean number of photons 1. And also, if we check what happens for a given transmission, for example 1.8, if we lower the mean number of photons, we find that we can achieve radios that are at least 1.4. For higher transmission, higher input mean number of photons, we can have radios that are as high as 2. What's important to say is that the previous estimator is unbiased and that this estimator using threshold detectors is biased. But this bias tends to 0 for large transmissions, so we can always find a good situation. So thank you very much for watching this video. You can find our complete work in the archive, and please don't hesitate to ask any questions. Thank you.